Hey there, this is problem set number 6, where we introduce the idea of a mole and learn how we use it in chemistry. So, just talking about the definition of a mole. If you think about it, if I write a reaction, let's say I write CH4 plus 2O2 makes carbon dioxide and 2 waters. Okay, this is the combustion of methane, natural gas. This is the reaction of burning it. If you look here, technically we got like 1 there and a 1 in front of carbon dioxide. What this means is that one molecule of CH4 reacts with 2 molecules of O2 to make 1 molecule of CO2 and 2 molecules of water. That's awesome, but if I want to run this reaction and I want to get the correct amounts of everything to run it, I would have to go out and measure 1 molecule of CH4. I don't know how to measure something that small. So it would be nice if we had a way of talking about atoms and talking about molecules in amounts that are actually reasonable and practical for us to deal with. So, so a mole, the technical definition is a mole is the number of carbon-12 atoms in 12 grams of carbon-12. What that number is 6.022 times 10 to the 23rd. So basically what we do is we define this number, this giant, I think 10 to the 23rd, that is a giant number. And we define that number so we can talk about molecules and atoms in amounts that are large enough for us to measure and handle in real life. In other words, it takes a ton of molecules or a ton of atoms to get an amount big enough that's a reasonable amount to deal with. Why did we pick this number? Well, if I look at the periodic table, I know that the average carbon atom has a mass of 12.011 AMU, or atomic mass units, per atom. So each atom of carbon weighs that many atomic mass units. So what we do is we said, well, let's pretend we only had carbon-12. How much would we need to have 12 grams of it? And we figured out we had this number. Well, what that does is it means whereas the average carbon atom weighs 12.011 AMU, 1 mole of the average carbon atom weighs 12.011 grams. Okay, so this number is useful and was picked so that the atomic mass on the periodic table works in units of AMU per atom, but it also works in units of grams per mole of that atom. Okay, so that's why we use that number. What are the units on and come on. Why is this not working? There we go. What are the units on this number? First off, this number is called Avogadro's number, so you hear that a lot. But what are the units on it? Technically, the units are things per mole of things. The reason I'm saying things is because 6.022 times 10 to the 23rd is a number that represents a mole, but a mole could be of anything. And this brings us to 1b, where it says, in principle, we could use more familiar unit dozen in place of mole when expressing the quantities of particles, atoms, ions, and molecules. Okay, because similar to moles, a dozen literally just means 12. Right? It doesn't matter what you're talking about. You could have a dozen of anything. It's exactly the same with mole. Okay, but a mole, instead of being 12 things, is 6.022 times 10 to the 23rd things. Okay, and so really this could be atoms per mole of atoms if we're talking about atoms. If we're talking about molecules, we would be molecules per mole of molecules. Okay, so we'll use it later on, but you'll see the units don't really change the math that you're doing, but they should be correct to show that you understand what you're talking about. All right, what would be the disadvantage of using dozens to describe atoms, ions, and molecules instead of using moles? The disadvantage is kind of what we talked up here. 1 molecule of CH4 is too small to do anything with. 12 molecules of CH4 is still too small to do anything with. So I'm just going to say 12 is still not enough atoms to measure. So, right, so 1 mole of carbon, 1 mole of carbon is 12.011 grams. That's very small, even still. And so even when we have a 10 to the 23rd of the thing, it's still pretty small. So a dozen would be way too small. All right, so let's kind of get some context of moles, and we're going to use it in the context of M&Ms. Hopefully this emphasizes the fact that the mole itself doesn't have anything necessarily to do with atoms or molecules. It's just a number of stuff. So if you had 1 mole of M&Ms, how big would the box need to be to hold all of them? Assume the volume of a single M&M. I don't know what that A is. Let's see. Assume, oh, that's supposed to be a little registered trademark. Candy is about 2.2 centimeters cubed, and calculate the volume of the box in kilometers cubed. All right, so what's our ending unit? We want to get to kilometers cubed. What's our starting thing? 1 mole of M&Ms. So I'm going to write 1 mole of M&Ms. Well, how many M&Ms is 1 mole of M&Ms? Well, 1 mole of M&Ms is 6.022 times 10 to the 23rd actual M&Ms. We're trying to get to kilometers cubed, okay? And we know that 1 M&M is 2.2 centimeters cubed. So let's just apply that right now. We know we're in units of M&Ms right now, so I could say 1 M&M is 2.2 centimeters cubed. I'm now converted from M&M units to volume units in centimeters cubed. But I want to get to kilometers cubed. I'm going to do that in 2 steps. I'm first going to go to meters. And I know that there's 100 centimeters in 1 meter, but I'm not doing centimeters and meters. I'm doing centimeters cubed, so I need to cube these. Now I've gotten to meters cubed, and now I want to go to kilometers cubed. I know 1 kilometer cubed is 1,000 meters cubed. Sorry, 1 kilometer is 1,000 meters, so I cube all of that to get kilometers cubed to meters cubed. When I do that, my calculator I got a big number. I can have 2 significant figures. Actually, technically I only have 1 mole of M&Ms. So I guess, but I'm going to use 2 significant figures because I can. 1.3 times 10 to the 9th. I'm taking this to mean that you had exactly 1 mole of M&Ms, which is why I'm using the 2 significant figures. So 1.3 times 10 to the 9th kilometers cubed. Hopefully you recognize that is a very big box, and therefore should tell you that 1 mole is a very big number. So now we're going to assume the box from part A is a cube, and all the sides are equal length. Is the side of the box closest in length to the diameter of the Sun, diameter of the Earth, diameter of length of state of Texas, length of Utah Lake, or width of the BYU Marriott Center? So basically we've got a cube. We know the volume of it. We know all the sides are the same length. Well, the volume is just side times side times side. If they're all the same, volume is side cubed, which means the length of the side is volume to the 1/3, or the cubed root of volume. So I'm just going to say the length of the side is going to be 1.3 times 10 to the 9th to the 1/3, which is the same as saying the cubed root. And that got me 1091 kilometers, but I only have 2 significant figures, so really I should have 1100 kilometers, which is closest to the length of the state of Texas. So a box that's literally as long or as wide as Texas is. So that's how that should, again, wow, Texas. That should give you a good idea of how much stuff we're talking about when we're talking about a mole. All right, calculate the molar masses of the following common flavors in food. So these are just different molecules with their elements there. So if I want to calculate the molar mass, all I have to do is add up all the molar masses of all the atoms. So I've got 8 carbons plus 8 hydrogens plus 3 oxygens. And that's going to give me 152.15 grams per mole. You could also say AMU, but I'm going to say grams per mole. Now, not too worried about sig figs here. So I'm following the exact same process for all of these, so it'll be 10 times 12.011. I just don't want to write it all out. This one is 164.20. So what I was saying is significant figures all depends on how many decimals you use for the molar mass. So I'm just not worrying about it. Usually when you're calculating molar masses, it'll be in the middle for use in a different problem. So you'll just want to make sure that you use enough significant figures to calculate it, that it doesn't limit the number of significant figures that are in your problem. So you just look at how many significant figures should be in your problem, make sure you use more than that when calculating the molar mass. Now we're going to do the exact same thing with these 4 sweeteners. Nitrogen has a molar mass of 14.007 and sulfur has a molar mass of 32.06. And just one more reminder, because of how we define mole, when you use these numbers on the periodic table, the units could either be AMU per atom, or in this case molecule, because these are molecules, AMU per molecule, or they could be in grams per mole. All right, and now this next question asks, if you had 1.5 moles of each substance, calculate how many moles of oxygen each would contain, which would contain the most moles of oxygen. Okay, how to do this? Well, 1.5 moles. If we look at this vanillin, one molecule of vanillin has 3 atoms of oxygen. So 1 dozen vanillins has 3 dozen oxygens. So 1 mole of vanillin has 3 moles of oxygen. So I can just say if I have 1.5 moles, I know 1.5 moles of C8H8O3. I know that 1 mole of C8H8O3 has 3 moles of oxygen, which means here we would have 4.5 moles in vanillin. So really we're just taking all these subscripts and multiplying them by 1.5, which would give me, this would be 3 moles of O2 or of oxygen. This one would have 1.5 moles of oxygen. This would also have 1.5 moles of oxygen. This one would have 11 times 1.5 gives me 16.5 moles of oxygen. 4.5, 7.5, and 9. So then it asks which one would have the most. Well, because I've done the math, that's easy. It would be sucrose, but it would be just as easy without doing the math to just look at the molecules, and whichever one has the most oxygen in it will then have the most oxygen when you have 1.5 moles of everything. Okay, number 4. Suppose pairs of balloons are filled with 10 grams of the following pairs of gases. Which balloon in each pair has the greater number of molecules? Or atoms in the case of AR, because AR is just an atom. Okay, explain how you know. Alright, we've got 10 grams of these things. Same mass of these things. Which one has more molecules? Well, if you think of it, let's say I had 10 pounds of bricks and 10 pounds of feathers. Do I have more bricks or more feathers? Well, I have more feathers because each feather is lighter, so you need more of them to add up to 10 pounds. Well, if I've got 10 grams of each of these things, whichever one's lighter, will have more. So I just calculate the molar mass. If I do that real quick, CO2 has a molar mass of 44 grams per mole. NO has a molar mass of 30 grams per mole, so I have more NO. CO2 again is 44. SO2 is 64. Therefore, more CO2. And here O2 is 32. Argon is 40. So I'd have more O2. Hopefully that's simple enough. Alright, if you had equal masses of the substances in the following pairs of compounds, which two would contain a greater number of ions? Because we don't know what, well, ions are just charged particles, but I'm just going to replace this with atoms. The answer is exactly the same. It just makes more sense to ask about atoms at this point in the class. So this is very similar to the one before, right? Except now we have to take into consideration how many atoms each of these would break into. Right, so let's say that we had 1 gram of each thing. Well, NABR, actually I'm going to drag this over here. And I'm just going to write out one of these for you to see how we would solve this problem. And I'm going to write out this guy. So let's assume that we had 1 gram of NaCl and 1 gram of MgCl2. And I want to get number of atoms. Well, I know that 1 mole of NaCl from the periodic table, if I add it up, is 58 grams. And then 1 mole of NaCl has 2 moles of atoms. I could do the same thing here. 1 mole of MgCl2 is 94 grams. 1 mole of MgCl2 has 3 moles of atoms. So this problem becomes different because the previous problem you only had to worry about the masses. But now, because it's asking about atoms and not molecules, we have to break it down one more step and think about how many atoms are in each molecule of these. So when I do this math, I get this has 0.0345 atoms in 1 gram. I picked 1 gram. You could pick any mass you want because all we're doing is seeing which one has more. This one has 0.0319 atoms, which means NaCl has more atoms. So that would be the answer here. Now in this case, both of these have 2 atoms, so I could just look at the molar masses. Let's do that real quick. NaBr has a mass of about 103, and KCl has a mass of about 75.5. Okay, and which means if we had equal masses, we would have a greater number of KCl atoms in KCl. Over here, CrCl3 has a mass of 158.5, and Na2S has a mass of about 78. Which means if we were to do something similar right here, if we had 1 gram CrCl3, 1 mole has 158.5 grams, and 1 mole of CrCl3 has 4 moles of atoms, which would give me about 634 atoms. If I had 1 gram of Na2S, 1 mole of Na2S is equal to 78 grams, and 1 mole of Na2S has 3 moles of atoms. So this should really say moles of atoms. It shows moles of atoms. If I wanted to find the actual number of atoms, I would have to multiply that by Avogadro's number, but I don't need to do that in order to compare them, so I'm not going to. Realizing that, I realized that I multiplied here instead of divided, so that number is not correct. It's more like it. I got 0.025, so it looks like Na2S comes away with the bigger number of atoms. Right, hopefully that made enough sense. The first one, you didn't have to think about how many atoms were in each molecule because they asked for the number of molecules, but here they asked for the number of atoms, or ions, but at this point it's exactly the same thing. So, so we had to take that into consideration. All right, number 5. Although they are not too common, there are US $1 coins. These are the so-called golden dollars, which bear the likeness of Sacagawea or past US presidents. The composition of these golden coins is given by the US government as 6% zinc, 3.5% magnesium, 2% nickel, and 88.5% copper. How many atoms of magnesium are there in a Sacagawea dollar coin that weighs 8.1 grams? So what's our starting unit here, or starting value? Well, we know our coin is 8.1 grams. That's how much coin we actually have. the end of the day, we want atoms of magnesium. So this first step is going to be figuring out how much magnesium there is in this coin. And we know there's 8.1 grams total, and it is 3.5% magnesium. So if I multiply those together, I get 0.2835 grams magnesium. So now I can just start with that number, and now we're going to try and get that to atoms. Did I say magnesium? Sorry, I should have been saying manganese. We're now going to try and get that number into atoms. Well, we have this process of getting from grams to moles to atoms. And you're going to end up doing this a lot. There's a lot of things they could give you that you can then get to grams in multiple ways. And after we get to atoms, there's a lot of things they could ask for. But this process of going from grams to moles to atoms will always be the same, and there's only one way to do it. Well, we really only do it in one way. Okay, so if I have grams and I'm asked to get atoms, I'm going to have to go through moles. So how do I get from grams to moles? Well, there's a conversion factor to get from grams to moles, and that's the molecular weight, because it's in units of grams per mole. So up here when we were calculating molecular weights, grams per mole, that's the conversion factor to get from grams to moles. It's how heavy 1 mole of that thing is. Then once we get into moles, we got to get to atoms. Well, what do we use there? Well, that's Avogadro's number, because it tells us how many things or atoms are in 1 mole of atoms. Okay, so that process isn't going to change. You're going to do it the same way every time. So in this case, they give us, or we're starting with grams of manganese. We're trying to get to atoms of manganese, so we're going to have to go through this process. So the first thing is to use the molecular weight. Molecular weight of manganese is right there on the periodic table. So we know 1 mole of manganese weighs 54.938 grams. And then we're trying to get to atoms. We know that 1 mole of manganese is 6.022 times 10 to the 23rd atoms of manganese. So I can simply plug that in. And I got, with 2 significant figures, 3.1 times 10 to the 21 atoms of manganese. There you have it. All right, moving on, number 6. How much is there? Number 7, that's it. Okay, number 6. A common gem size used in wedding rings is about ½ a carat. A white diamond in my wedding ring is 0.536 carats. Given that the density of white diamond, pure form of carbon, is 3.5 grams per centimeter cubed, and 1 carat is 200 milligrams, how many carbon atoms are in my ring? How many moles of carbon? So we know we're trying to get to carbon atoms, and they're giving us masses. So we've got to get to grams, and then we can follow this process. So what is the actual amount of diamond or of carbon that I have? ½ a carat, or no, 0.536 carats. We know we're trying to get to grams. Well, they tell us carat to milligram, so 1 carat is 200 milligrams, and we know there's 1,000 milligrams in 1 gram. So now I've gotten to grams, and now I can go through this process because I'm trying to get number of moles and number of atoms. Well, I know that 1 mole of carbon, that's what this diamond is 12.011 grams. So if I were to stop here, which I think I will, if I were to stop here, I'd get the number of moles of carbon. that, I got 0.00. How many sig figs? 3 there, 3 there. Yep, so 3, 8, 9, 3 moles of carbon. And then I would take it one more step to get to atoms, because I know 1 mole of carbon, 6.02 times 10 to 23rd atoms. And that gives me 5.37 times 10 to the 21st atoms of carbon. So again, same process that we did above. You got to get whatever they give you into grams, and then you take grams to moles with the molar mass and moles to atoms with Avogadro's number. All right, the Cullinan diamond is 3,106.75 carats. Largest gem quality rough white diamond ever found. How many diamonds, like the one in part A, could the Cullinan diamond have been used to make? You could overcomplicate this problem, but we know that this diamond weighs that much, and the diamond in part A weighs that much. So if we want to figure out how many we could make, we have that many carats divided into a bunch of rings that weigh this many carats. And so if we did 3106.75 divided by 0.536, you would get 5,796 rings. Here I have 6 sig figs, there I have 3, so really it's 800, but I need 3 significant figures, so 5.80 times 10 to the 3 rings. Sweet. All right, number 7. 2 inorganic blue pigments are Han blue and Egyptian blue. Which has a higher molar mass, and by how much? Okay, so in order to do this, we are going to have to calculate the molar masses. There's an easier way to do it, but I'm just going to do it the hard way, calculate the molar masses. So we've got Han and Egyptian. Pull my periodic table. So Han blue is going to be, whoops, barium, so copper, silicon, and oxygen. And I got a molar mass of 473.206 grams per mole. Egyptian, the shorter way to do this is just to recognize that the only difference between the two molecules is that first atom. And so you could just figure out the difference between the molar masses in that first atom, but I'm going to do the whole thing because I think we need to for the second part anyway. this molar mass is 375.94 grams per mole. All right, and so then they want, which is a higher molar mass, so Han is higher, and by how much? Well, 473.206 minus 375.954. It's bigger by 97.252 grams per mole. And if you look, you can see that's just the difference between barium and calcium's molar mass. All right, if you had a 10-gram chunk of each pigment, one in your right hand and one in your left, which sample would contain more copper atoms? How many more copper atoms would it contain? So again, there's an intuitive way to think about this, but because they want a specific number, let's just do the math. So I have 10 grams of Han, and I have 10 grams of Egyptian. And I want to convert it from grams into copper atoms. All right, 10 grams of Han. Well, I know the molar mass of Han is 473.206 grams per 1 mole. And I know that 1 mole of Han has 1 mole of copper in it. And then I want to get all the way to atoms. I know that 1 mole of copper is 6.022 times 10 to the 23rd atoms of copper. So now I do that math. 10 grams. And I get, in 10 grams of Han, to 7 times 10 to the 22nd copper atoms. Alright, now with the Egyptian, I know that 1 mole is 375.954 grams. And I'm going to do this one a little bit differently. You could do it exactly the same as I did up here, but I'm going to change this first to molecules of the dye. Molecules. So why did I use Avogadro's number here and say atoms and here and say molecules? Well, because I was in copper, units of copper. Copper is an atom. So when I change it to mole, or change it from moles, it turns into atoms. This Egyptian dye is a molecule, so when I change it from moles, I'm going to change it into molecules. But then I would say 1 molecule of the dye has 1 atom of copper in it. Again, just 2 variations of doing the exact same thing. The math ends up being exactly the same regardless of what you do first. 1.60 times 10 to the 22nd copper atoms. So which one contains more copper atoms? Looks like Han does. Wait. Sorry, nope. Egyptian. Right, because it's a bigger number, obviously. And then how many more? If I just do the math, 1.27 times 10 to the 22 is 1.6. 0 times 10 to the 22, I get 3.3 times 10 to the 21. Which, let's see. enough. That's the right answer. That's the difference in copper atoms. So really the takeaways that you need to get from this problem set are getting comfortable converting between grams to moles and moles to atoms, as well as understanding when we're talking about moles, understanding how these numbers in a chemical formula relate to the amounts of atoms. They also relate to the amounts of moles of atoms, and kind of getting comfortable with that terminology. There you go. That's problem set 6 about the mole.